purpose of this lecture is to introduce the nature and the effects of turbulent flow. I shall assume that you have some background in elementary fluid mechanics. I should like first to identify the phenomenon and to illustrate some of its effects, and then to take a partial look at its dynamical structure. The time available prevents us from taking anything other than a qualitative account, and prevents me from mentioning the names of many of the people who have worked and are still working to improve our understanding of the phenomenon. I won't attempt a formal definition of turbulence. The words most characteristic of it are random and rotational. We may say that turbulent flow is a random rotational motion that's always observed to occur when fluids flow in a state of shear at sufficiently high Reynolds number. The Reynolds number, you'll recall, is the dimensionless ratio of inertial to viscous forces in a shear flow. Density, velocity, length, viscosity coefficient. When the Reynolds number is very small, the viscous forces are dominant by definition, and they damp out any fluctuations that chance to occur. In fact, it was just in this connection that Osborne Reynolds, the British engineer, first discovered the significance of this dimensionless product that now bears his name. You've all seen smoke blowing out of a stack in irregular, billowing motion. Here's a jet of tobacco smoke. The chaotic character of both the motion and the smoke distribution is evident. This is typical of turbulent flow. The same sort of thing, of course, occurs in liquids. Here's a familiar sight: water flowing downward from a glass tube at low velocity. In this case, there's no turbulence. The flow is in the state we call laminar. The rod of water has a smooth, glassy appearance. If we increase the Reynolds number by increasing the rate of flow of water, we find that the edges of the liquid jet become blurred. A short duration photograph reveals a completely different surface structure. Many other technological and natural flows involve turbulence. For example, the high-speed camera catches an irregular mottled pattern in the wake of a bullet. The scrambled eggs that we see behind this bullet are index of refraction fluctuations that occur because of the temperature fluctuations in the wake. These in turn are generated by viscous dissipation. In geophysical flows, turbulence is also very common. Here are some time-lapse movies of cloud motions. The evidence of atmospheric turbulence most familiar to you is probably the gusty dispersal of smoke from a stack. If you lived downwind of this stack, you'd be very concerned with the likelihood that the smoke might get into the neighborhood of your house. The pertinent mathematical function is the probability density for the smoke particle displacement. If you live downwind of two or more stacks, the pertinent mathematical functions would be much more complicated. For example, with two stacks, you must be concerned not only with the individual probabilities, but also with the joint probability that the smoke from the two stacks might come into the neighborhood of your house simultaneously. Going on to still larger scales, we find that certain galaxies and nebulae have the general appearance of a turbulent puff or swirl of smoke. In fact, some current theories of the origin of the universe begin with the assumption of a relatively uniform distribution of matter in space, effectively a fluid in turbulent motion. Then it's assumed that the galaxies and the stars resulted from gravitational instabilities due to density fluctuations set up by this turbulent motion. One of the most practical effects of turbulent motion is its ability to promote rapid mixing. The spoon in a coffee cup is primarily a turbulence generator. Here's an experiment illustrating a mixing operation at two different Reynolds numbers. Starting with approximately the same initial conditions and stirring at about the same rate, we shall find much more rapid mixing in the case of the low viscosity fluid than in the case of the high viscosity fluid. The difference is the higher Reynolds number and therefore the incidence of turbulence. The irregular turbulent motion draws a relatively concentrated blob of fluid out into increasingly tenuous filaments, which then are relatively easy prey for the molecular transport properties. In the case of the high viscosity fluid, the same motion of the spoon generates only a laminar flow, which draws the filament of cream into a long string without additional convolutions. We've now looked superficially at two of the principal effects of turbulent flow: its dispersive or diffusion power and its mixing ability. The former was shown in the self-spreading of the turbulent smoke jet and in the dispersal of smoke from a stack. A natural method of mathematical description for such a transport phenomenon is one which deals primarily with the statistical history of the motion of the smoke particles. This is a so-called Lagrangian framework for the fluid motion. In fact, such a Lagrangian approach has actually been used by G.I. Taylor the British engineering physicist, in a pioneering work on the kinematics of turbulent diffusion, published as far back as 1921. Unfortunately, the dynamical equations in the Lagrangian framework are so complicated that no one has yet succeeded in giving them a full treatment. Looking at turbulence in the usual fixed or Eulerian coordinate system, the diffusion can be understood in a model qualitatively like molecular transfer. Suppose we have a mean temperature gradient indicated in the sketch with a random fluid motion convecting heat back and forth between hotter and colder regions. There will necessarily be a net transport rate down the gradient. If the turbulent velocity fluctuation is of order v, and the blobs of fluid remain coherent over distances of order L, then the associated temperature fluctuation will be this increment L times the temperature gradient. In that case, the average rate of transport down the gradient per unit area must be of order V times the temperature fluctuation L dt bar dy. In terms of a gradient transport model, in which the heat transfer rate is given by a diffusivity times the gradient, a comparison of these two expressions for the transport rate shows the diffusivity to be approximately V times L. The first attempt to represent turbulent transport as a simple gradient process was made by the French engineer J. Boussinesq about 70 years ago. The more elaborate model I've described here was introduced by Taylor in England and Prandtl in Germany about 35 years ago. It is called the mixing length theory, named after this characteristic length L. We have known for many years that these Eulerian models are far too simple to be quantitatively correct. Nevertheless, they may serve as methods of qualitative reasoning and may even serve as a skin into which a more correct theory can be stuffed at some time in the future. In general, the turbulent diffusivity is much larger than the molecular diffusivity. The only likely exception is heat transfer in the flow of liquid metals. Momentum transfer is perhaps of greatest concern to us because it involves forces and therefore the motion of the fluid itself. The great excess of turbulent transfer over laminar transfer means, for example, that when a body has a turbulent boundary layer on it, it suffers much greater drag forces, skin friction forces, than when it has a laminar boundary layer at the same Reynolds number. And by the same token, when a pipe has a turbulent flow in it, it has much greater pressure loss than with a laminar flow at the same Reynolds number. The extreme complexity of turbulent motion makes it foolhardy to attempt analysis by following in detail the motion of each differential fluid element. Instead, we seek only certain appropriate average values. This means that we're dealing in a problem in statistical mechanics. The fact that we use a statistical approach doesn't make the work more difficult. In fact, it makes it simpler, because we lower our goals, and instead of seeking highly specific and detailed information, we do seek only certain average functions. The modern statistical mechanics of the physicist is unfortunately still not able to cope with the problems of turbulence mechanics. Two typical difficulties, for example, are first the impossibility of defining a permanent particle of the fluid to deal with, and secondly, the fact that the phenomenon of viscous flow is always dissipative. In other words, there's a continuous viscous dissipation of energy from turbulent kinetic energy to internal energy of the molecular motion. The simplest statistical functions to describe the flow field are just the mean velocity functions. A time record of one component of the instantaneous velocity at a point may look something like the sketch. If we have a sufficiently long record in time, there will be no difficulty in defining an average value. For example, in this case, we can define the time average as an integral limiting process. Of course, we're very much interested in the statistical properties of the deviations from this mean value, for these deviations are just the turbulent velocity fluctuation. The simplest non-trivial average value or statistical value of this turbulent velocity is just its mean square. And the ratio of this to the square of the mean velocity is a measure of the ratios of the two kinetic energies. The square root of this ratio is what we call the turbulence level. Of course, at any instant of time, the turbulent velocity is also non-uniform in space. Considerably more detailed statistical information is given by the energy spectrum. This gives a statistical measure of the distribution of energy with respect to the various eddy sizes. It is, in effect, a Fourier analysis of the turbulence signal. If we consider a random turbulent velocity signal in time and perform a Fourier analysis on this, we have no fundamental frequency in higher harmonics as we have in the case of a musical note, which is a periodic signal. Instead, the energy is distributed among all frequencies. Therefore, the turbulent energy spectrum can be represented as a continuous curve. The contrast between these two kinds of signals is marked to the ear. Here we have a sound rendition of a musical note and a turbulent velocity signal where the turbulence has been picked up by a hot wire anemometer in a turbulent jet flow. Of course, the turbulence is also non-uniform in space, and therefore the spectral analysis method applies equally well in space. Here, a turbulence spectrum relative to wave number in space has the same general appearance. K1, the wave number, plays the same role in spatial analysis that frequency does in time analysis. Now, of course, the energy distribution with respect to wave number or with respect to frequency, when integrated over all wave numbers or all frequencies, gives the total energy in that corresponding velocity component. Since the turbulence is three-dimensional in space, of course, a one-dimensional Fourier representation is incomplete, and we must deal with a three-dimensional velocity spectrum. A lot has been done with the spectrum up to this time, but in turbulence research, we must sometimes deal with even more complex statistical properties. Turning now to the dynamics, the chief feature of turbulent motion is its dependence on the nonlinearity of the system. Most of the fluids we deal with move in good approximation to the Navier-Stokes equations of motion. Here they are, written in Cartesian coordinates. T is the time, x, y, and z the displacement, u, v, and w the velocity components, p the static pressure, rho the density, nu the kinematic viscosity. These equations express Newton's second law. du, dt, and the other unsteady terms are the unsteady acceleration. These are the convective acceleration terms, static pressure force, viscous force. The key terms are these convective acceleration terms, which you see are quadratic in the velocity components. When these terms are negligible, which corresponds to small Reynolds numbers, no turbulence can occur. This means that we expect no such thing as a linearized approximate theory of turbulence. In essence, a nonlinear system is one in which the output is not proportional to the input. Here's a sketch of an instantaneous response linear system with a straight line transfer function, a nonlinear system with a curved line transfer function. In a linear system, any particular Fourier component remains independent of all others and lives out its life in ignorance of them. In a nonlinear system, on the other hand, we have continuous interactions among the Fourier components. This can be illustrated by feeding a purely sinusoidal input into a linear and a nonlinear transfer function. The output of the linear system contains only the original wavelength. The output of the nonlinear system is distorted and must contain higher harmonics which were not present in the input. The same kind of thing can occur if we deal with a system that obeys a nonlinear differential equation. Here's a nonlinear equation that has the same general character as the nonlinearity of the Navier-Stokes equations. The development of higher harmonics in the case of a nonlinear system of this type can be illustrated if we start with an initial distribution which is purely sinusoidal, and for small times express theta of x and t as a power series in t, limiting the series just to the linear term. The time derivative can be expressed in terms of the function and the space derivative by looking at the original differential equation. With the initial sinusoidal distribution, we see theta 0 is a sine wave, d theta dx a cosine, the product of which gives, of course, the sine of twice the wave number. Therefore, for small times, we have not only the original sinusoidal field, but the second harmonic. And of course, as time proceeds, higher and higher harmonics become important. Now, this suggests that in turbulent motion, there must be a continuous transfer of energy from the large structure to the small structure. although a simple model like this doesn't rule out the possibility of some reverse transfer. Very crudely, we can represent this energy transfer process as a series of boxes, one for mean motion kinetic energy, one for turbulent kinetic energy, and one for the internal energy of molecular agitation. The transfer to internal energy is the dissipative action of fluid viscosity. In more detail, we might split the turbulent kinetic energy box into a chain of small boxes representing a distribution of eddy sizes. More correctly, this whole transfer process must be represented in terms of continuous curves. In the physical space, a continuous spectral migration from large to small structure shows up if we look again at homogeneous mixing. For simplicity, suppose there's no molecular diffusion. Starting with a relatively large and coherent volume, the turbulent convection distorts the dye into ever more convoluted and filamentous shapes. This tenuous structure, involving thinner and thinner sheets and lines, evidently corresponds to smaller and smaller wavelengths in the dye concentration field. To how high a wave number will this spectral transfer process go? I think we can see that the very thin sheets and filaments will be smeared out rapidly by the molecular diffusion. The equivalent statement in turbulence dynamics is that the smallest eddies will be killed off very rapidly by viscous dissipation. This can be analyzed by defining a spectral Reynolds number, R sub k, in terms of a characteristic velocity, characteristic length of the spectrum, and the kinematic viscosity. From dimensional reasoning, the characteristic velocity must be just the square root of the turbulent energy spectrum times the wave number. And of course, the characteristic length, L sub k, must be 1 over the wave number itself. Therefore, the Reynolds number is 1 over nu times the square root of E over k. Now we know that for the high wave numbers, the turbulent energy spectrum decreases with increasing wave number. Therefore, the turbulent spectral Reynolds number must decrease with increasing wave number, indicating that for the small structure, viscosity, viscous forces, become increasingly important, which confirms our previous conclusion. This also leads us to the conclusion that if we start with both large and small structure in a fluctuation field, after the first small interval of time, only the large structure will remain. A quantitative estimate of the relation between the turbulent small structure, characteristic length, and the mean free path of the molecular motion can be gotten by comparing the mean free path to the length which corresponds to a Reynolds number of unity. In this case, we represent Reynolds number as 1 V star, L star is the corresponding characteristic length and velocity, and the kinematic viscosity. From kinetic theory, we know the kinematic viscosity is representable as the mean free path times the molecular velocity c, and from this equation we get an estimate, the mean free path over the characteristic length of the turbulent small structure, which is of the order V star over c, the Mach number of the smallest eddies. And of course, in subsonic flow at least, this is an extremely small number. Another basic property of turbulent motion is its general tendency to become isotropic. That is, for the appropriate statistical functions describing the motion to lose their sense of direction. In the turbulence, this comes about chiefly through the effect of static pressure, which is a non-directed effect. But we can illustrate it through the use of the example of mixing. Here, as the isotropic mixing process goes on, the dye structure gradually loses its principal direction. Turning now to turbulent shear flow, it's a well-established fact that the large structure of turbulent shear flow is not an order of magnitude smaller than the width of the shear zone. This means that the large structure can't possibly be isotropic. However, the energy in this large structure is rapidly transferred down to the finer eddies. And it turns out that this energy cascade process is one in which the preferred direction is gradually lost. So if we have a turbulent shear flow at large enough Reynolds numbers, giving a long enough energy cascade, the small structure of the turbulence may indeed be isotropic. This notion of local isotropy was introduced to turbulence theory by the Russian mathematician A.N. Kolmogorov about 1940, and has since received a fair amount of experimental verification. In giving you a syndrome for turbulence a little while ago, I mentioned rotationality. Now, of course, the quantitative measure of rotationality in a fluid motion is the vorticity, which is just the curl of the velocity vector field. In many cases, it's more appropriate to describe the turbulent motion in terms of vorticity rather than velocity. And in fact, turbulence may be regarded as a random field of vorticity. From your general mechanics, you know that angular momentum is conserved in the absence of tangential forces. This fact is put to good use by a figure skater who increases angular velocity, which is vorticity, by starting with a large moment of inertia and reducing it by pulling in arms and legs. The mixing illustration in the turbulent motion demonstrated to us that fluid lines tend to stretch. Now, if we consider that vortex tubes or vortex lines in the fluid motion are also fluid lines, and forget viscosity for the moment, as they tend to stretch and conserve their angular momentum, the vorticity associated with a particular line going from this state to this state will necessarily increase. Therefore, in the absence of viscosity, vorticity would increase without limit. Of course, in a two-dimensional flow, the vorticity is necessarily conserved because the vortex lines can't stretch. Therefore, two-dimensional turbulence, if it could exist, would be relatively uninteresting. The magnification of vorticity by vortex line stretching is of considerable importance in the generation of hurricanes. This weather system involves weakly swirling inflow toward a rising central column. Viewed from above, the inflowing air is reducing in diameter with a corresponding stretching of vertical vortex lines. Like the figure skater pulling in his arms, it spins faster as it reduces its moment of inertia. As in other areas of science, research on turbulent flow proceeds by both experimental investigation and theoretical analysis. In fact, the combination of these two approaches is as essential to progress as two legs are for walking. With an instrument like the hot wire anemometer, which senses local velocity fluctuations, we are able to measure the statistical functions that reveal the internal structure of the flow. From the theoretical point of view, we try to account for the observed results with a minimum number of plausible assumptions. At the same time, we attempt to make predictions on the outcome of experiments yet to be done. The common history of research in almost any area starts with the asking of relatively superficial questions about the complex cases that we encounter in the outside world. With increasing progress, we ask more sophisticated questions of the simpler and simpler cases we can define. In fact, a very important talent is that of dreaming up cases of maximum simplicity. Yet they must not be so simple that we throw out the baby with the bathwater. As I indicated a little while ago, that might happen if we attempted a linearized theory of turbulent flow. A most fruitful theoretical simplification has been the notion of isotropic turbulence introduced by G.I. Taylor. Remarkably enough, this simplest of turbulent flows can be realized approximately in the laboratory, in the flow behind a regular grid. On the other hand, there is a continuing urgency to learn to predict the behavior and effects of turbulent flow under the relatively complex circumstances of technology and nature. Therefore, we must continue to channel a certain amount of effort into the study of these practical flows even before we have achieved a satisfactory understanding of the simplest ones.